of my favorite techniques for evaluating integrals is exploiting symmetry in some way. Now, exactly what I mean by that depends on the integral, but typically this involves some kind of trick or manipulation where we can get the answer without actually ever doing any integration. It feels a little bit like cheating, and it's always a really cute phenomenon. So the integral I want to demonstrate that with is this one right here. The integrand is log of x over 1 plus x squared. The kind of trick that I'm about to do is pretty necessary here because if you want, you could think about trying to just find the antiderivative of that function, and you're welcome to try. You'll probably have a pretty rough time though. In fact, I plugged this antiderivative into Wolfram alpha, and I'll show you what we get here. So here's the antiderivative. It looks pretty scary. There's complex numbers. There's also a capital Li sub 2. This is something called a di-logarithm function. Who knows what that is? And there you go. So the point is that trying to evaluate this integral directly by just finding the antiderivative is probably not the move. So we need to do something a little clever which exploits symmetry. I've given us a bit of a hint based on the bounds. Here's what we're going to do. I'm going to make a substitution exploiting the symmetry of the bounds. In particular, what I'll start out with is I'm going to let u be 1 over x. Like I said, to me this is motivated by the bounds, because if I make this substitution, it's going to reverse the order of the bounds. We'll see that in a second. In any case, we have a substitution. Let's see if we can transform the entire integral as usual. Now, anytime you make a substitution, you have to change everything. That includes the bounds, that includes the integrand, and that also includes the differential. So as usual, we can compute du. 1 over x is like x to the negative 1, so when I differentiate that, the power rule tells me that this turns into negative 1 over x squared dx. And then we'll see what we can do here. The problem is that, here if I solve for dx, dx is negative x squared du, and I can't really just plug that up in here. Nothing cancels out. So what happens in this kind of scenario is that you want to take your original substitution solve for x, which in this case would just be 1 over u, and then this is what we'll use to rewrite the integral accordingly. In particular, that thought bubble in red tells me that dx, which is negative x squared, x is 1 over u, so this is like negative 1 over u squared du. And now I've got dx entirely in terms of u. Likewise, we can use this fact to rewrite the integrand entirely in terms of u. So let's do that, see what we get. So the integral that we're working with, log of x over 1 plus x squared dx, after making this substitution, what happens? Well, first of all, the bounds, like I mentioned earlier, when x is 1 over e, what is u? It's 1 over e, which is e. Likewise, when x is e, u is 1 over e. Like I mentioned, the bounds kind of change order, and to me this is the motivation behind this substitution. Likewise, log of x up here we figured out is 1 over u, so this is log of 1 over u. And then in the denominator we've got 1 plus x squared is 1 over u squared. Dx we wrote up here as negative 1 over u squared du. Okay, so that looks a whole lot worse, but I think we can algebraically simplify this a little bit, and then we'll cross our fingers and see what happens. So there's a couple things we can do. The first of which, to me, is if I look at the log expression here, log of 1 over u is like log of u to the negative 1. Log of u to the negative 1, I can take that negative 1 power and bring it down in front. So the numerator there is exactly the same thing as log of u with a negative sign out front. Now I've got this negative sign here. Let me just pop that out there for the moment. Then the other thing I can do here is I have a u squared in the denominator. If I take this u squared and multiply across the denominator here, I'll pick up a 1 times u squared, which is u squared. And then here I've got 1 over u squared multiplied by u squared. That turns into 1 du. Looking better. Also, it's looking similar to the thing that we started with up here, and that's exactly the point. Let me do a couple more algebraic manipulations and we'll see what happens. Okay, so this is going to be a little weird, but here's what I'm actually going to do. I'm going to use this negative sign here to reverse the order of the bounds. So integrating from e to 1 over e with a negative sign out front, this is exactly the same as integrating from 1 over e to e. The negative sign here I can use to reverse the order. Now I've still got this negative sign, so this negative sign I'm going to pop out front. And then I'll leave the inside alone. U squared plus 1 is the same thing as 1 plus u squared. Okay, let's reevaluate and see what we've shown. This thing right here looks exactly the same as what we started with. The only difference is that the dummy variable is different and there's a negative sign out front. Because u is a dummy variable, I can just switch back to x. I could call this whatever I want. I could call it u, I could call it smiley face. I'll just call it x again, and here's the summary of what we've shown. This integral that we started with, 1 over e to e of log of x over 1 plus x squared dx, well, this is the same thing as negative integral from 1 over e to e log blah 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 blah. Here again I'm just going to switch back to x because it's a dummy variable and it doesn't matter what I call it. And then notice this is exactly the same as this. Treat this like an algebraic equation and solve for the integral that we want. How do we do that? I would add this term to both sides. And when I do that, I would have the integral plus the integral, which is 2 times the integral from 1 over e to e of blah, 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 blah. And this equals 0. Divide by 2, and we're done. The integral that we started with is 0. Like I said, it feels like we didn't actually ever do any integration. In particular, we never found this crazy looking antiderivative. We just exploited symmetry of the bounds and some weird symmetry of the integrand to get what we wanted. Pretty cute.